Okay, good morning, year 11s. Welcome to another lesson in intermolecular forces. Uh, Before we move on to what we have planned today, I need to do a quick review of what we did in the last class. Um, if you remember, we talked about groups of electrons, and we talked about how the groups of electrons will determine the shape of a molecule. Uh, these are a few key points that I would appreciate if you take down in your notebook. If you have a single covalent bond, just a single bond, then you have two electrons, and that counts as one group of electrons. If you have double covalent bonds, which are four electrons, they still count as one group of electrons. If you have a triple bond, six electrons in total, they still count as one group of electrons. And a lone pair will count as one group of electrons as well. So to have more than one group of electrons, you have to have separate bonds. Key point. There has to be separate bonds or separate lone pairs. Only then you will have more groups of electrons. Now, once you have taken this down, I will move on to how we use the groups of electrons to determine the shape of a molecule. So I'm going to stop the recording until you have taken this down. Okay, so moving on from this bit here, we need to talk about how the groups of electrons determine the shape of a molecule, and that can be done by using these simple rules. Uh, if you have one or two groups of electrons, and these one or two groups could be in the form of a double bond or a single bond. If you're wondering what that means, is I'll give you an example. You could have something like carbon dioxide. Now, how many groups do you have here? How many groups in total do you have? You can answer. Two groups. And the rule states that if you have two groups, one or two groups of electrons, that gives it a linear shape of one, and it has a 180-degree bond angle. You will expect that. Why? Why would you expect a linear shape when you have uh, two groups of electrons? Can anyone raise their hand and answer this question? Yep, please. Loudly, please. Yep. So they arrange themselves so that they are furthest apart from each other. So that's how. That's an example of a linear shape. The the second rule is that if you have three groups of electrons and no lone pairs, now this is key. You cannot have lone pairs here. If you have lone pairs, it will not have the same shape as just having three groups. Three groups of electrons and none of which are lone pairs gives a triangular planar shape. And same reason, once again, they will arrange themselves so that they are as far apart from each other, and that turns out to be a triangular shape. We call it triangular planar, but you will find that in some books it is also called trigonal planar. I'll give you time to write. Let's just go through the rest of the rules. Four groups of electrons, no lone pairs, will arrange themselves in a shape, in a three-dimensional shape. So this is a three-dimensional shape called tetrahedral. 109.5 bond angle. If you have four groups of electrons and one of these is a lone pair, then you have an angle which is less than 109.5, and you have a shape called a pyramidal shape. An example of this is given here. A very famous example of this is, well, let me get this from someone in the class. Michael, I think you talked about it in the last class. What was that example that you were giving, which would have a pyramidal shape? NH3, beautiful. So example is NH3. Good work, Mike. What's the angle for tetrahedral? 109.5, sir. Now, last but not least is when four groups of electrons and you have two lone pairs. Now, if there were four groups of electrons, you would expect it to be what shape? Just 4 groups of electrons. Tetrahedral. How, and you'd expect a bond angle of 109.5, but that isn't the case here. Why? Because you have two lone pairs, and the repulsion between lone pairs and lone pairs is so strong that it is stronger than the repulsion between bond pair, which are the electrons here, and the bond pair. The repulsion between lone pair is stronger than the repulsion between lone pair bond pair, and it is even stronger than the repulsion between bond pair and bond pair. And because of that cumulative effect, the repulsion between lone pair and lone pair and lone pair and bond pair, what happens is your angle decreases from 109.5 to somewhere around 106, 107.5. A good example, a very famous example of this kind of shape, a V shape, is anyone? Yes, Michael's on fire. H2O. So now you have the time to note all this down. I'm going to pause the video until you note this down. So if you've taken all the rules down now, you should be comfortable enough to practice question 2 and question 3 from set 24, Essential Chemistry by Lucarelli. Once you've done that, I'll move on to the next topic. Thanks. Okay, so now we move on to the concept of electronegativity and covalent bond dipoles. So the first thing that we need to talk about is what is electronegativity. And electronegativity is a concept that we learnt about during the first term when we did periodic trends. So if you're struggling to remember what that was, you can quickly go back to that chapter and look it up. But I'm going to ask people if they know about the concept, if they can define electronegativity. So if you could please raise your hands for an answer. Yes, Lisa. It's the ability for an atom to draw electrons to itself. Beautiful, beautiful, Lisa. Thank you. So it is the ability of an atom to draw electrons towards itself. Does anyone remember which element or which atom has the greatest electronegativity? Okay, yes. Towards itself. Example, chlorine. And do you know what its value is on the Pauling scale? 4. Yes, beautiful, Callum. Okay, now let's quickly talk about what a bond dipole is. A bond dipole shows the electrons, where the position of the electrons in the bond that is formed between two elements. It shows which element has a greater pull towards the electrons, and where are the electrons in that bond. So if you look here, we have a chemical compound that we know as hydrochloric acid. Hydrogen obviously has a very low electronegativity, and you can look that up in a Pauling scale. I think hydrogen has about 2.1 on the Pauling scale, and chlorine would have a 3.0. So you would expect the electrons to be pulled towards chlorine, and once that happens, when the pair of electrons is pulled towards chlorine feels as if it has a strong hold on the electron, so it gets what we call a partial negative charge. Delta stands for partial negative charge, which basically means that chlorine partially holds the electrons toward electrons. Similarly, in contrast, hydrogen will get a partial positive charge. That means it has hydrogen feels as if it has lost the electron partially. I mean, it's not completely lost it because it still has some part of it pulled towards it, but again, most of it is towards chlorine. So hydrogen gets a partial positive charge. So that's what a bond dipole is. This would allow you to go through question 4 in set 24. Same thing, you're marking it yourself. I'll give you, let me have a look at how big the question is. I'll give you 5 minutes to go through it. Thank you. Okay, so we finally move on to polar and non-polar molecules, which is an extension or an application of the concept you just learned, that is on dipoles. So I'm going to start off with a basic question here. What are polar molecules? What are polar molecules, and give examples. So any ideas what polar molecules are? Let it be a sensible answer. Yes.
Where there's a differentiation in electronegativity.
Beautiful. So are you saying that this is a polar molecule?
Yeah, same. You could bond chlorides. Like carbon.
Is this a polar molecule? There is charge differentiation, right? Yep. Okay. There is, and where are the electrons being pulled?
To the chlorine.
To the chlorine, right? To the chlorine. Not a polar molecule. It is not a polar molecule.
Does it have to be at each end?
No. Okay, let's do another one. Let's do another one. Carbon dioxide. Come on, this must be a polar molecule, right? Charge differentiation. Oh no, it's not. It isn't. Ooh. Oh, let's do another one. Sulfur dioxide.
It's going to be a comedy teaching.
Is this a polar molecule?
Probably not.
Yes. No.
Yes,
It's
no?
going to be positive at one end and negative at the other.
Is it? Is it? Is it?
No, it's not. No, it's not.
It's not a polar molecule. And so on and so forth. There are very, okay, so polarity is not only dependent on the bond dipole, which you thought it was. Yes.
Is it like where one has a partial negative and one has a partial positive charge?
Yeah. So, oh, a polar molecule.
Yeah.
Yeah, it is, and I'm not disputing the definition. It is when you have a partial positive and a partial negative charge. What I am disputing here is that these are not polar molecules based on the definition. A polar molecule by itself will have a partial positive and a partial negative charge. Agreed. But polar molecules not only depend on the partial positive and a partial negative charge, they also depend on the shape of the molecule. Now, if you look at this question, the one example that I gave, carbon dioxide, what's the shape of this molecule? So oxygen's pulling the electrons here. Oxygen's pulling the electrons here. What's the net effect? Where is the electron going to go?
It's going to go on the sides.
It's going to be in the center, dead center. And if it is dead center, there is no charge differentiation. If there is no charge differentiation, it's not a polar molecule. A polar molecule requires charge differentiation, but charge differentiation is also a function of the shape of the molecule. If the shape is such that the charge differentiation or the dipoles cancel out, then there is no charge differentiation. So the dipoles shouldn't cancel out. An example where the dipoles don't cancel